Hi, let's go through the solutions just for page 60. Right, a force diagram for a water skier and then a vector addition diagram. Moving at a constant speed. When I do my force diagram, I've got in my head what my vector addition diagram might look like as well. So I'm kind of, even though I'm drawing one, I'm kind of thinking at the other one at the same time. So here's my system. Obviously, force of gravity on skier by Earth. He's not accelerating downwards, so there must be some opposing force from, looks like the water. Force normal on skier by water. You can see there's a force being applied by a rope. Let's make this really big. And a force applied by a rope is called a tension force on skier by rope. And I know he's moving at a constant speed, so in my head I've got to be thinking about that. What does that mean? It means that there is a balanced force coming back. Force, and that's probably going to be from the water. Friction on skier by water. Those ones are equal and these ones are equal. To see with my equality marks how two lines here and one line each here to show that they're equal but not equal to the vertical ones. Vector addition diagram, I redraw it. I go one at a time. I don't need to label them. I'm happy to not label them, so I'm going to go like that. I'm just going to work around, so that's my first one, and I'm going to go down here, that. So down, head to tail, and it shows that we get back. We started here, we ended here, net force is 0. Great. Force diagram for the sled and the kids. I'll do my force diagram here, give myself plenty of room. Okay, as always, I'm thinking about what the vector addition diagram looks like. As I do my force diagram, I might have to update some things. Obvious one, force of gravity. I'm just going to say I'm going to call this whole thing of the kids plus the sled, I'm going to call it a system. So it's the force of gravity acts on everything on the system by Earth. They're moving at a steady pace. Now I know, obviously I know what the answer is because I'm the teacher, but I'm going to go through probably what you're thinking is here, and we'll explain what it means. You probably think, a normal force equal and opposite. That normal force, because it's a contact between the ground and the sled, so it's not on the system, it's on the sled by ground. Then there is a tension force, and you can see that goes up at an angle. Force tension on sled by rope. It's going at a steady pace, constant speed, so there must be some backwards force. And that obviously is going to be friction on sled by ground. Right. This is where this one, you'll see, my thinking wasn't quite right. When I go to draw my force diagram, my vector addition diagram, I'm going to start here and work my way around. Force of gravity. Let's label them so we know. Force of friction. I said my normal force is as big as gravity. And then my tension force is up to here. Go away. Now wait a second. This is a steady pace, so there should be, go away, no net force. However, this force vector addition diagram starts here and ends here, and that suggests there is a net force. In this case, it suggests that there is one upwards. So I've done something wrong here. But this is the point. I made this question hard on purpose, so you would be thinking about that. It turns out, for this to be a nice cancelled out vector addition diagram, when I pull something up at an angle, I kind of lift it off the ground a bit. When I lift it off the ground a little bit, there's not as much normal force. So my actual force diagram here, my normal force is not the same size as my gravity force, it's smaller. It's just this big. So if I was to draw this again, force of gravity, force of friction, normal force is small. Then look, when we put our tension force in, gets back to the start. What a tricky question, Mr. McGovern. Draw a force diagram for the table. The dancer is leaning on it at an angle while stretching. Label the force vectors. Right, let's go through the same thing. You noticed in the last one, because I knew the answer, I was kind of in my head, I was going between the force diagram and what the vector addition diagram was looking like at the same time. Even though I only did this one first, and then I had to fix them up, didn't I? To go back and forth. We'll do the same thing here. Right, the table has, down here, obviously, force of gravity. On table by Earth. It has a normal force. Now I know the answer, but I'm just going to put this in anyway, and we can go back and figure it out later. By ground on table. Normally they're the same size, aren't they? This person's pushing down in this direction, pushing down at an angle. A pushing force is just like me sitting on the ground. It's a normal force. So there's a normal force on table by person. And because I'm kind of pushing in that direction, but the table doesn't slide, it's just sitting there, there must be some sort of friction. Friction can only ever go along the surface. Okay, so I've got to figure out what my other ones are to account for that, but friction is always, if you look back a few pages at our definitions, friction is always parallel. Friction always parallel to surface. So here's my friction. On table by ground. Now I got to do my vector addition diagram. The table's not moving, so I'm expecting my vector addition diagram to show me no net force. Let's see what happens. Let's start with the upwards one. I just randomly chose it. Doesn't matter which one you start with. If normal, I'm then going to go around and just do them around my friction. My gravity I've said is the same size as F normal. And then I've got another F normal from the person down here. Ugh, that doesn't seem right. Now last time when I looked at changing things, I changed the size of my normal force. The reason I changed that instead of my gravity force is gravity doesn't change. The Earth pulls on you the same no matter how hard something else is pushing on you. The Earth doesn't know that something else is pushing on you. Because the normal force, it depends on atoms getting squashed together. So with this one here, with the rope, as I lift the sled off the ground, the atoms aren't squashed as much, so normal force changes. The same thing happens here. So the gravity, I can't fix this by making gravity different size. The only way I can fix this is by making the normal a different size. So that's obviously wrong. I've got to make my normal, by the look of it, has to be bigger. My normal has to be bigger. So let's cross that out. And let's make the normal here bigger. So now I've got a bigger normal force. Got my friction. Got my gravity. And I've got my other normal from the person's hand. Now that makes sense. There's a bigger normal force because the table's getting squashed into the ground more. The ground's being compressed more, so it pushes back more. So these are tough. In fact, these are tougher than you're going to get in level 2 in your exam. I've never seen anything nearly as tough as these. So if you understand these ones and you can get around your head around these, you're going to be smashing it. So well done. I'll see you for tomorrow's lesson.